Hi, in this video, we're going to be looking at some rational functions. We're going to start out with something that we actually learned a little bit earlier, probably in your last class, but we're going to revisit this because it is a common misunderstanding. A rational expression is just like a fraction, but it's a fraction with polynomials. So a rational expression is a ratio of two polynomials. Notice when we have the ratio of these two polynomials, we can't have 0 for the denominator because a fraction with 0 in the denominator is not defined. To find those places where the function is not defined, a lot of times what we need to do is factor these expressions out. So again, common errors that I don't want you to make. We have two expressions for a simplified version of this, 2z minus 4 over 2z squared. And we want to see which is the correct version. So we will go ahead and we're dividing two things here. What we're going to do is we're going to try to factor things out that we can. Notice the numerator has a greatest common factor of 2. I'm going to factor that out. I'll get z minus 2. And then I have a 2 times z squared. The only time we can cancel from numerator to denominator is when we have two factors. I'm going to cancel the 2's, and we will have z minus 2 over z squared. So it does turn out that this first version is correct. So the bad thing to do would be to try to cancel the z and the 2's here, because you are trying to cancel over addition and subtraction. So we won't even think about doing something like that. Okay. Now, when we have that factored, we can see exactly where the function's undefined. It's going to be when those denominator values of z are equal to 0. So in this case, it would be 0. Next thing we want to do, and this is going to come into effect at the end of this video, is we're going to sometimes want to combine two rational expressions together. Again, you've probably done this, definitely earlier in the class, but probably in your last class. The way that we combine these together is to find the least common denominator, LCD, of those two fractions. And the best way to do this is to factor those polynomials out. I'm going to start, we're going to try to combine these together. So I'm going to start by trying to factor these out. I notice in my numerator, which I really don't have to do my numerators because I'm trying to find a denominator, but I do notice that I could take an x squared out. So if you want to just note that, you could say x squared, and that's going to leave me an x plus 3. That's actually not going to be very helpful to us, but we are looking for those denominators. So I know that x times x is equal to x squared. I'm looking for two things that multiply to a negative 15, but add to negative 2. So factors of 15 are 1 and 15, 3 and 5. Oh, there it is. So I'm going to do negative 5 plus 3, because when I add those together, I get the negative 2. Now I see that my least common denominator is x minus 5. There it is again, so I just need one of those. And then x plus 3. So what I'm going to do is I'm going to take this second fraction and I'm going to build it up over that least common denominator. To do that, I just multiply by the x plus 3 and the x plus 3. Let's go ahead and work this over here. I'll have x cubed plus 3x squared all over that least common denominator, minus 4x times x is a 4x squared. 4x times 3 is a plus 12x. 5x times x is a plus 5x. And 5 times 3 is a plus 15. Now I have that build up over that common denominator. When I have two things build up over a common denominator, that means I can add the numerators together. So I'm adding sort of like things together here, and I can do that. If you want to note, this actually does combine together to give me a 17x. So when I'm doing this over a common denominator, I'm going to just write that down here in factored form. I need to be really careful with this minus. This minus is going to distribute through all these terms. I'm going to write this down one more time before I simplify things out. I'm going to have an x cubed plus 3x squared, but then I'm going to have a minus 4x squared. I'm going to have a minus 17x. I'm going to have a minus 15. So you see this minus goes through every single term. And when I combine things together here, I have an x cubed. I have 3x squared minus 4x squared. I have negative 17x and minus 15. So notice I have combined these things into one nice fraction here. I can also tell, since the denominator is simplified, that x can't be 5 or negative 3, because that would be what would make these factors in the denominator 0. Now we're going to be looking at some new stuff, and we're going to start with the domain. We talked about a rational function being a ratio of two polynomials, and that denominator, q of x, can't be 0. So to find the domain, we're going to weed out all these numbers where the function isn't 0. So with rational functions, we don't have to worry about anything else except for where that denominator is 0. And we weed that out. Unless it's a word problem, we of course don't want it to not make sense in a word problem. So I'm going to actually set each one of these equal to 0 and figure out where it happens. This one will be equal to 0, so that denominator is equal to 0 at negative 5. So x can't equal negative 5. That means my domain would be negative infinity to negative 5 union negative 5 to infinity. So only one spot where it's not defined. Here I'm going to go ahead and try to factor out the denominator. So again, this one shouldn't be too bad. I have x and x, so I need two things that multiply to 18, negative 18, but add to 3. So I need a plus and a minus. Factors of 18 are 1 and 18, 2 and 9, a little bit off, 3 and 6. Ooh, that seems good. So what about plus 6 and minus 3? So 6 minus 3 is 3. Boom, we have it. So the denominator is going to be this. If I set that equal to 0, then I find out x will be 0 at 6, and negative 6, my apologies, and 3. So I can't include those. So here my domain is going to be negative infinity to negative 6, union negative 6 to 3, union 3 to infinity. So essentially these three intervals will weed out those 2 points if we're looking at interval notation. Finally, in C, I set that denominator equal to 0. This one looks like a good quadratic formula, or even better, square root method. So I'm going to subtract over my 25. I'm going to take plus or minus the square root of negative 25. That negative means that I have an I coming out, and the square root of 25 is 5. So I have plus or minus 5i. But those aren't zeros that we can actually plug in this function. They're imaginary zeros. So here in this case, we can't have them being imaginary, but we wouldn't plug anything imaginary into this function anyway. So our domain in this case would be all real numbers, or if you'd like to express it in interval notation, negative infinity to infinity. All right. The next thing we're going to look at is what these zeros symbolize. Vertical asymptotes. Hi, it turns out for each one of these points that aren't in the domain, we are going to have an undefined point in our graph. Usually what it's going to represent is called a vertical asymptote. To understand what a vertical asymptote is, we need to sort of figure out some notation that they will use in our textbook, but also if you go on further into math. These symbols with arrow notation essentially means x, as x approaches a, there's a plus up here, from the right. So we're approaching that function from the right-hand side. We're approaching that value, that x value, from the right-hand side. I have a graph here. So if my value a is right here, in this case at -5, as I go to -5 from the right, this function is getting bigger and bigger and bigger. A minus superscript means approaching some number a from the left on the x-axis. So again, if I approach -5, but this time from the left, when I get closer and closer and closer to that point, my function goes down to -infinity. And we've seen this actually within behaviors of graphs. Not really the plus and minus symbology though, so that means right and left. What we have seen is that, for instance, within behavior, as x goes to infinity, that's the right-hand part of the graph here, and as x goes to -infinity, that's going to be the left-hand part of the graph. So when we're looking at a vertical asymptote is going to be a vertical line, x is equal to c, where c is just some number. If f of x, so as we get closer to that, f of x increases the magnitude without bound. What that means is f of x goes to infinity or -infinity as x approaches that number from the right or from the left. And so points in which the rational function is undefined are exhibited by this vertical asymptotes, or holes if the function's factors cancel in the graph. A graph of a rational function cannot intersect a vertical asymptote. So if we're trying to find the vertical asymptotes of functions, the first thing we need to do is figure out where that domain is, or where that domain is undefined, or where that denominator is equal to 0. So in this case, we know that the denominator is equal to 0 at x is equal to -5. So x equals -5 must be a vertical asymptote, or it's going to be a hole. So -5 is our point A, or as they describe C here. So this is actually the graph of the first function. Here's -5. So if I'm going to -5 from the left, so as x goes to -5 from the left, let's see what's happening. So I'm coming from the left, and I can do a trace. And if I plug in like a -5.1, I have -10. If I plug in a -5.01, I'm getting closer, I get -100. So I'm way down on the graph. If I plug in a -5.000001, so I'm getting really close to -5 from the left-hand side, then I get this huge negative number. This is like -10 billion, I think. So we see that as x goes to -5 from the graph from the left, that our function is going to -infinity. That sort of tells us that this is a vertical asymptote. I should also check, so with these rational functions, they'll do the same thing from both sides. So I should check, or they'll go to infinity or -infinity from both sides. So I should check from the right side. So if I use this function and if I plug in 5. Let's do something a little bit bigger. Let's do 5.11. Well, that wasn't even close, right? I needed something close to -5. So how about from the right-hand side, -4.9? Okay, let's try something even less than that, or greater, I should say, -4.8. All right, so -4.8, it's getting close to -5 from the right, but we have a 5. -4.9, it's getting bigger. negative 4.99, bigger, 100, negative 4.9999999. Whew. Oh no, a trillion maybe. So we see that that is going up to infinity. So what's going to happen here is at that point, x equals -5, we're going to have the graph have not be defined. And it's going to have this vertical asymptote here. So we can say that in this case, we have a vertical asymptote at x equals -5. And we can illustrate that with a vertical dashed line. We'll do that later. Really, we don't have to use the calculator on each one of these. We can just figure out where they're undefined. But we have to be careful of those because this time we have to factor both numerator and denominator to see if terms cancel. Because if terms cancel, then we have what we call a hole. So I'm going to factor this numerator, and I get 2 times x squared minus 2x minus 3 if I take a 2 out of both all three terms here. And now I have something that factors even further. So this is going to be an x and an x. I need two things that are going to multiply to -3, but add to -2. Pretty simple, right? It needs to be 1 and 3, but 1 and -3 would add to the 2, so that would work. So notice what's happening here. I have this plus 3. Okay, my apologies. This should actually be x plus 6 and x minus 3. Thought I had it good to go, but I had this denominator factored incorrectly. So now you sort of notice that when I compare the numerator and denominator, I have factors that cancel. So if I cancel those out, I would get 2 times x plus 1 all over x plus 6. But there's actually going to be a point here at -3 or 3 that I can't plug in and get a function. So what's going to happen here is we see if terms cancel out, there's going to be a hole where those two terms canceled out. So there's going to be a hole at x is equal to 3. And since x plus 6, this doesn't cancel out, there's going to be a vertical asymptote at x is equal to -6. Let's just go ahead and verify that on our grapher, since we have it out. So I'm going to put in the original function here, parentheses 2x squared minus 4x minus 6, in parentheses divided by x squared plus 3x minus 18. And now if I graph, you can definitely see that there's a vertical asymptote there at -6. But you can't see any hole there at 3. How do we know it's there? So this is where your calculator doesn't come in much handy. You really have to do the algebra to figure this out. Let's verify that these are undefined there, though. So if I do a trace, if I plug in -6, I should get undefined, and I don't get any value out. So that's where this asymptote is. Now, if I put in 3, I also get undefined. So over here at 1, 2, 3, there's actually, you can't see it, but there's this hole in the graph, which isn't defined. Okay. Notice as we get closer to 3, though, from the left and the right, we don't go to infinity and negative infinity. We actually go to a y value, and that y value would actually be this function with 3 plugged in to the simplified function. So what is that? 3 plus 1 is 4 times 2 is 8. 8 over 3 plus 6 would be 8/9. So about 8/9 would be the where the hole's y value would be. And you can sort of see that if I plug in something like 3.000001, we get 0.88888891. So 8/9 as a continued fraction, or sorry, as a decimal is 0.8 repeating forever. So, if I even got closer, like 2.9999999, in terms of the calculator, that's really about 8/9. Okay. Finally, this last one we saw, it's undefined nowhere. So this one's going to be solid on its whole domain. So here we have no vertical asymptotes. The next thing we do with a rational function is look for its end behavior, and that's going to lead us to horizontal asymptotes. All right, the next thing we're going to be doing is looking at finding the horizontal asymptotes, which will be our end behavior. So again, using our terminology above, we've actually looked at this, but we say the horizontal line, y is equal to some number, is a horizontal asymptote of the function if that as the function value approaches that number, as x goes to the left-hand side of the graph, so negative infinity, or x goes to the right-hand side of the graph, positive infinity. With rational functions, that number c will actually be the same for the left and the right. So what we can do, this is what I like to do, is I like to sort of look and see what controls the numerator and denominator, and that's the degree of the function. So I'm looking at the degree of each of these. When I look at the numerator, I only have one term there, so this is sort of like a 1. And then the degree of the denominator is 1, x to the first. So really, this function looks like a 1 over x function at the ends. That's the key. So really what we can say is as x goes to plus or minus infinity, that function sort of looks like this. And as x gets bigger and bigger and bigger, like 1 over 2, that's 1/2, or 1 over 3, that's 1/3. I like to look at it as a pizza problem. So let's say that I have one pizza and I'm sharing it with our class. That might be 1/30th of a piece, or of the pizza each. We split it evenly. That's a little bit. But what if I'm really generous and I split it with all of JCCC? So one pizza for 30,000 people, we really won't get anything left. So if I have something that's constant, no matter how many pizzas I had, if I split it evenly over infinitely many people, this will always go to 0. We'll always get really none left. So in this case, we can say that the horizontal asymptote, or the end behavior, is going to be at y is equal to 0. And I'm pulling this graph back up just to sort of show you that that's sort of the case. You can see, like, if I trace as we go to negative infinity, so I'm just going to do -10. And you can see that, this is 0.2. So if I went to like -1000, okay, it's outside the, the domain of the function, but trust me, it's going to be smaller. If I put in something like 10, I'm going to the right-hand side, yeah, I'm getting really small. I get 0.066666. All right, so you can see that on both ends, that y value is approaching 0, or the x-axis. What happens with g of x? So I see here, as x gets bigger and bigger and bigger, this square controls the numerator, this square controls the denominator. So this is actually like a 2x squared over x squared. This is actually like a 2, 2 over 1, or a 2. So I should see for this function that we should be going to 2 on both sides as we get bigger and bigger and bigger, or very negatively large. So as x goes to plus or minus infinity, these terms don't matter as much. It's the ones that have the x squared that are going to take over in the long run. So this might happen slowly, but the function is going to go to 2. So what we can say is we have a horizontal asymptote at equal to 2. And I did go ahead and plot this, so let's give it a look. If I turn this one off, I go to this next one, graph it. There's our graph with the hole in it. And again, it's not going to maybe be totally obvious because we're just going from -10 to 10. So if I, whoop, if I do a trace first, and then if I plug in -10, well, this is still at 4.5, so we're not there. If I sort of scroll along and get smaller, or more negatively large, I should say, for x, you can see the y value, you know, it's getting smaller and smaller. But you can't really see that. You would have to go way far out to see that we do have an asymptote actually at 2. So sometimes a better way to see this is through the table. But before we do that, let's go back and do a zoom standard and just show that it does sort of approach 2 on the right-hand side too, as well. So once it plots, I'm going to do a trace. And these horizontal asymptotes are important because they sort of tell us what happens, in the long run with things. So some of these models can actually be modeled by rational functions. And if we want to know what happens at the long term, we can find those asymptotes. So again, you see it's getting bigger, the y value is getting bigger, but 2 is not obvious. So what we can do, if we really want to, is we can go to table. I'm going to go to table set, and I'm going to ask for my x values, my independent variable, and have it just chug out my y variable. So if I go to table, if I plug in some x values, so I want to see what happens when I'm at -10, -100, -1,000, -1,000,000. Okay, so with all intent and purposes, this is 2. But if I go and scroll over, you see it's close to there. So yeah, you can see that that's actually approaching that. Now going to the right-hand side, what happens at 10? What happens at 100? What happens at 1,000? What happens at 1,000,000? It goes pretty much to 2. In fact, mathematically, we can see it goes to 2. So here's a mathematical way to show it. Here is a good check with your calculator to show that that does work. But it's important to know what's happening mathematically over here. Okay, let's look at this last one. So if I'm looking at the degree of this one that's factored out, I really look at the degrees of each one of these. I have a 2x, I have an x and an x. 2x times x is 2x squared times x is a 2x cubed. The denominator, really the x squared, is taking over. If I cancel these out, I have a 2x. So in this case, as x goes to plus or minus infinity, my function goes to 2x. And as x gets really, really big, or really negatively big, this is just going to go to infinity. So in this case, there's going to be no horizontal asymptotes. This one's going to look more like a parabola at the end, at least, as it's going to go up to infinity or down to -infinity on both sides. All right, so we have all the constituent parts ready to graph these things. That's our goal. So in the next sort of section, we're going to be looking at systematic way to do that in a couple examples. I want to quickly touch on this last one that we did, where we didn't have any horizontal asymptote. We do note that the degree of the numerator, 3, is exactly 1 greater than the degree of the denominator, 1. And we saw that this didn't have a horizontal asymptote. In the case where we have 1 degree greater, where we end up with something just times x, we actually get a line as in behavior. So depending on how far we go into the graphs of these, we can actually determine what's happening a little bit better. So these are what we call oblique asymptotes. And oblique asymptotes or slant asymptotes are actually going to be as x gets bigger and bigger and bigger. If we divide those two functions together, we get y is equal to 2x, as we saw here. So we don't worry about the remainder, but we just take our quotient when we divide those. And it turns out that line y is equal to 2x is going to be an oblique asymptote. So really what that means in terms of our graph here, that we don't know from this analysis what really happens in the middle here. But at the ends, we do know that if I have a line, y is equal to 2x, so my slope is 2, so over 1 up 2, over 1 down 2. I have this line y is equal to 2x. I know that eventually my graph, as x gets bigger and as x gets more negatively large, my function is going to go into that asymptote. So it might look like this. It might do some weird stuff. It might actually cross the graph here. I'm not really sure without graphing it more. But at the ends, as x gets bigger, this function is going to go into that slant asymptote y equals 2x. Okay, I just wanted to mention that. So now we can sort of put these together because we're going to want to plot these. We've learned a lot about finding these things. So when I have a rational function, notice that the numerator and denominator don't have any common factors. The first thing I do to plot these is I find the vertical asymptotes. The graph of f of x has vertical asymptotes at the zeros of the denominators, as long as these have no common factors, so my poles have been canceled out already. The graph of f of x has either one or no horizontal asymptotes determined by comparing the degrees of the numerator and denominator. It turns out if the degree of the numerator is less than the degree of the denominator, then we saw that as we get bigger and bigger or more negatively large, the denominator takes over in weight, and y equals 0, or the x-axis, is our horizontal asymptote. If these degrees are the same, so like we had an x squared over x squared, then actually the ratio of their leading coefficients is going to be the horizontal asymptote. If the numerator is bigger than the denominator, there isn't going to be any horizontal asymptotes like the last one we just saw. However, in the case where the numerator is 1 greater than the denominator, we have an oblique asymptote or a slant asymptote. So keeping that in mind, here's how we graph rational functions. So we can use this sort of cookbook recipe on any rational function. The first thing we're going to do is find and plot the y-intercept, if any, by just evaluating f of 0. So we're going to plug in 0 and find the y-intercept. That's usually a cheat point. We're going to find zeros by setting that numerator equal to 0 and finding all the places that our graph crosses the x-axis, so those x-intercepts. We're going to find the x values that are excluded from the domain, if any, by solving that denominator is equal to 0. So we find where the denominator is equal to 0. Remember, if the numerator and denominator have any like factors, we first cancel these out, and these are wholes. We're going to then sketch these, and then we're going to find and sketch the horizontal asymptote of any using the rules we talked about above. We're going to test for symmetry. So sometimes this is pretty visual, but if we plug in f of negative x, and if we get f of x or negative f of x, then we're going to have symmetry there, and we can get one side for free by just plotting the other one. This is important. We're going to plot at least one point between and one point beyond each x-intercept and vertical asymptote. So these x-intercepts and vertical asymptotes are going to separate where we plot our points to fill in the curve. We're going to use smooth curves to complete the graph between and beyond the vertical asymptotes. So 7 steps there, but if we do these, we can successfully graph. a rational function. Let's try it. All right, so here we go. We're going to put our knowledge to the test. We are going to try to plot the graph of this rational function, and we are listing the steps over here. The first thing we're going to do is we're going to find that y-intercept. So to find the y-intercept, we let x equal 0. So if I plug in 0 for that function, I get 2 times 0 squared, all over 3 times 0 squared minus 9. That's going to be 0 over something that's non-zero. So I have 0, 0 as my y-intercept. I'm going to plot that right there. I'm going to find the x-intercepts. To find the x-intercepts, I look at where the numerator is 0. So for this, I would divide by 2. I would note that x squared is equal to 0 and use that square root method to find that x equals 0 is 0 of multiplicity 2. All right, hey, that's the same point we have here, so nothing new. I'm going to find the domain. So to find the domain, I look at my denominator, and I try to figure out where that is 0, and I weed out those points. I have a difference of squares here, so I need two things that multiply to 9, but add to 0. In fact, multiply to -9, but add to 0. So that's a +3 and a -3. And so it turns out when I put each one of these factors equal to 0, 3 never equal to 0. X minus 3 equal to 0 gives x is equal to 3. And x plus 3 is equal to 0 gives x is equal to -3. So my domain is going to be all those real numbers except for those 2 points. So when I write my domain out, I'm going to have -infinity to -3 union, -3 to 3 union, 3 to infinity. I take out those 2 points. And notice that these 2 points don't cancel out with anything in the numerator of the function. So that is going to be where my vertical asymptotes are located at. X is equal to 3 and x is equal to -3. I'm going to go ahead and plot those. These are going to be indicated by vertical lines with dashes. There's x is equal to 3. X is equal to -3. All right. I'm going to look at the horizontal asymptote. So if I bring the function back into play here, k of x, it sort of looks like 2x squared over 3x squared. Those are the degrees. Or 2/3 as x goes to plus or minus infinity. So it gets really big or negatively large. So it turns out that y equals 2/3 is going to be our horizontal asymptote. Another way you could have figured that out is just looking at the degree. So if I multiplied this through, I'd have 3x squared minus 27. And I notice that I have the same degrees in the numerator and denominator. So the ratio of my leading coefficients is going to give me that horizontal asymptote. So if I plot y is equal to 2/3, that's going to be right around here. Going to be a horizontal line, about 0.666. So closer to 1 than 0 on the y-axis. All right, and now I'm going to test symmetry. So to test symmetry, I'm going to use k of -x. If I plug in -x, I have 2 times -x squared, all over 3 times -x squared minus 9. The question is, does that give me k of x back or negative k of x back? Well, -x squared is just x squared. And same thing down here. So it does turn out that that is just k of x. sort of see there, hopefully. There we go. So k of x is equal to k of negative x. So this is going to be an even function. And that's a game changer. It's huge. Because that means if I plot the graph on one side, then it's going to be the same as the graph on the other side. So this has y-axis symmetry. All right. So now the last step I need to do is I need to figure out some points between the asymptotes and the x-intercepts. So really, I'm going to need to plot something on this interval, something on this one, here and here. However, I know that this is an even function, so really if I do one side, the other side's going to be exactly the same. That's why it's so huge to see that it has some symmetry. So I'm just going to choose a point like -10, and I'm going to plug that in. So I'm going to find k of -10. K of -10 is going to be 2 times -10 squared. That's 200 all over 3 times -10 squared minus 9. So essentially, I will need to figure out, is this positive or is it negative? It turns out that this one's going to be positive because I have 200 over 3 times 100 minus 9. That's 91 times 3. So this one's going to be positive. And what I know is the graph is either going to look like this. My graph can't cross these vertical asymptotes, or it could look like this. And at the end, my graph has to go into these horizontal asymptotes. So since this is positive, I know that my graph is going to look something like this. Now I'm just sketching it, but it does have to go into this asymptote at the left side, and it can never cross a vertical asymptote, so it's trapped. Another reason I probably could have done that without even plotting this, because if it did do something like this, it would have to cross the x-axis, which would mean that I would have had to have another x-intercept, but I don't. So if you use that logic, we have to see now if the graph does something like this, or if it goes down. Here, we don't know because the graph could actually cross a horizontal asymptote, just can't cross a vertical asymptote. So I'm going to have to plot another point here, and I can do that. Let's go ahead and plot -1. So k of -1 is equal to 2 times -1 squared all over 3 times -1 squared minus 9. And that's going to be 2 times 1. -1 squared is 1 minus 9 is -8. -8 times 3 is -24. So really that'll be really small, but it's going to be negative. So we see on this side, it's going down to -infinity. Can't cross that axis. Finally, we would have to plot 2 more points here and here to see if this went down or up, and if this goes up or down like this. However, since we have this symmetry, we know that if we plot one side of the graph, the other side is going to be exactly the same. So that's a good help with this y-axis symmetry. So I know that it looks like this, and the sketching here, it should have the same shape on the right-hand side. There's one other thing that I want to sort of impress upon you, which I think is sort of cool. Remember these zeros with polynomial? They told us sort of what happened at the zeros. Notice that when we were finding the zeros, the x-intercept, I had a 0 of multiplicity 2. Multiplicity 2 essentially was like a parabola locally. It sort of meant that it hit the axis and it went back down. It didn't cross. So you can see that behavior right there. So I sort of thought that that was cool, and I wanted to mention that. you can sort of see by the multiplicity on the zeros what's going to happen. I did go ahead and graph this on my calculator so you could see that we got essentially the same thing. So the last step, if you have a calculator, you might as well go ahead and check out what you have. Now remember, you're going to have to find all these aspects of the graph, but the calculator gives us a good check. So how did I do? Not bad, right?